So, differential equations and solutions. So we're looking at basically the general feel, especially for a lot of stuff in differential equations, is you'll look at solutions, and also a lot of the stuff applies and is like a general look at several things that'll come up later, so that's why it's introduced here. Especially things like initial value problems, which you'll see are very common with differential equations. So in these first two examples, they're quite short because we're given psi and placed OD equals 0, like basically a normal form. So we're given this form and we want it to be a normal form, basically. We're given for these two. And that generally looks like this, where we go from, we have that mess of all the variables, I equals. This is what we're given is equal to x squared z plus 1 plus xy. 1 plus x times y, the whole thing. So this becomes, so we converted into t, y, and y prime from x, y, and z. And we basically converted the equals 0 form, so it's equal to t squared times y prime, because x squared is t, x is t, y is y, and z is y prime in these converted problems types. This one's not seen really often, but it is an interesting, theoretical, looks at what happens. You add 1 plus t times y, and that's all equal to 0, so that's placed OD, so we have it like that, and then we change this to normal form. So we have t squared times y prime equals negative 1 plus t times y, that's, you subtract that over to, we want everything in terms of just y prime, so we subtract on both sides that, and then we divide by t squared, so we get negative 1 plus t, we get 1 plus t product times y, as I say in parentheses, times y, divide by t squared, and it's a negative, the whole radical, the whole fraction. We're not talking about square roots, we're talking about just fraction, so it's a negative, this fraction. And that's the normal form, just in terms of y prime equals. And next when we do the same thing, we have xz minus 2y minus x squared. So we set up a ty, y prime in terms of ty and y prime, so it's t, y prime minus 2 times y minus t squared, and that's equal to 0. And we can add both sides, 2y and t squared, we can add that to both sides, so we get t times y prime equals 2y plus t squared, and then we divide by t, we get y prime equals 2y plus t squared divided by t, and that's normal form right here. It's just a different way of looking at something, and I think out of all things in this course, it's like one of the rarest things to look at. Obviously, but here's something that, you don't always usually show this, but it's an interesting concept as well. It's a good beginning to actually looking at solutions of differential equations, as you put it. So we showed that the given solution is a general solution of a differential equation. Pretty much we're given y prime equals negative t times y, and we have y at t equals c. That's the general solution, and c has a condition, it's basically negative 3 to 3 integers, so it's negative 3, negative 2, negative 1, 0, 1, 2, 3 is what the constant c can be, but that's not really important for this problem. But what we do is we have these two things. We have general solution, we have the differential equation. So y prime, we're just making sure that we get something where the left and right side agree. So we have y prime here. This green stuff is what yt is, so we do c times e to the negative 1/2 t squared, which is that c times e to the negative 1/2 t squared is what this thing is. So e is raised to this whole power here. And you'll see in the next section how this is actually a common form they have as a constant times an exponential, but not uncommon to see. But and we take the derivative of that, and that's to show that this general solution is in fact the general solution of the given of a differential equation. It's given. So it's equal to negative t here times the same thing basically, but without the derivative. Then you plug them in. So derivative of negative t squared divided by 2. We take the derivative of that times c times e to the negative 1/2 t squared. And that's because of how exponentials work. We're basically taking derivative. C is not factored in since it's a constant. So when you take the derivative of an exponential like this, then e raised to something, you do negative t squared. You basically take this, it's negative 1/2 t times t squared. You take the derivative of that, multiplied by the whole expression, exponential. It's a good review of that concept. And then we have the right hand side, which is just negative t times c times e to the negative 1/2 t squared. Then we follow this through and we have basically negative 1/2 times t squared. The derivative is just negative 2t over 2, because t squared is 2t's derivative. Negative 1/2 is constant. And the 2's cancel out and we'll basically have negative t times c e negative 1/2 t squared equals negative t times c e negative 1/2 t squared, and that's the same. So in fact everything clears. This what you're just showing this basically in a problem like this. You just show that this occurs. That you can actually show that the given solution is a general solution of the differential equation. Red and purple match. Now the purple is in fact the solution of red here. And 4 is the same way now. Y prime plus y equals 2t, and we have yt equals 2t minus 2t times 2tc. Oh no, it's 2t minus 2 plus. Sometimes that's the problem. You have to be careful with your pluses. Sometimes you mistaken for a t if you're not careful. Plus c times e negative t. This condition does not matter for these because we're not looking at like graphs or anything. If we were looking at a graph, this would actually be something to look at, but not here. So you plug it in. You plug in y at t into this expression, y prime plus y equals 2t. Derivative of y t plus 2 times, is basically plus y, and then it's equal to 2t. Eventually you get a situation where you have left and right side equal each other. 2t equals 2t. In this case. And that's after you do your rules of algebra and canceling out and everything, you'll get that. And of course the derivative in this one is, just to put attention to it, you have 2t minus 2 plus c times e to negative t, so derivative of 2t is, you do each one separately. Subtraction and addition can be separated. So you have 2, and derivative of minus 2 is just 0. So 2 plus c times e to negative t times negative t derivative. That's what really matters, because it's e to the negative t, so the derivative will be negative t's derivative, which is just negative 1. And that's why I end up with 2 minus c e negative t power plus 2t minus 2 plus c times e to negative t, and those cancel. You see, this cancel out with that. That's how it works. The work is there. And 5 is the same type of problem where we have, it's a little bit more work though. But it's something a little bit easier. Well, the sine and cosine derivatives are more commonly seen. They're seen in Calc 1 usually. So you follow the process through and you get the same stuff. Drawing attention to the exponential, it's e to the negative 1/2 t. So in that case, the derivative is just negative 1/2, because derivative of a constant times t is just 1. It's just a constant. And we're taking the derivative of what the e is raised to, what the exponent is. Whenever you do it, how this works, but same type of problem. We eventually get 2 cosine t equals 2 cosine t. And that's it for that type of problem, really. Or at least that exact one, just going over to showing that the solution is in fact for that differential equation. But implicit, so now we want to do a multiple plot problem where we show use implicit differentiation to show that t squared plus y squared equals c squared implicitly defines solutions of the differential equation t plus y prime equals 0, just y times y prime. And you do this quickly enough. You do t squared plus y squared equals c squared, which means, you have that. You start from there. and we plug in, as you can see here, you basically we have c squared, so at t plus y prime equals 0. So what happens is here, what was it? Oh right, we take the derivative. Sorry, I wrote this a while ago, sorry about that. So derivative of t squared's derivative is 2t. Derivative of y squared is implicit. So implicit differentiation, if you remember, it's 2 times y prime. That's how we do it here. And that's equal to 0 because c squared is just if you square 5 or 6, you get a constant. So the square of a constant is constant. See, any constant, so the derivative of a constant is 0. So we divide both sides by 2, and we get t plus y times y prime equals 0. So that's all you have to show. Yeah. You basically take derivative of t squared, the derivative of t squared plus y squared equals c squared, make derivative of the whole thing, and show that it's t plus it can be shown to be t plus y times y prime equals 0. And now we have to solve t squared plus for part b plus y squared equals c squared for y in terms of t to provide explicit solutions. Show that these functions are also solutions of t plus y times y prime equals 0. This one takes a little bit of work, but a bit more work than the last one, definitely. So we have that. We solve for y first, this expression. So y equals square root of c squared minus t squared. But then we have, so this is y equals c squared minus t squared all raised to the 1/2 power. So then we take the derivative for y, and we get y prime equals, we take the 1/2 down, and it's multiplied by this to the negative 1/2 power, because 1/2 minus 1 is negative 1/2, and you multiply by negative 2t because that's the derivative inside of the bracket of the parentheses is c squared minus t squared's derivative is just negative 2t. And 2's cancel out, and we simplify down to y prime equals negative t divided by square root of c squared minus t squared. Because negative exponential you can put in the denominator of a fraction. And the next step is what I wrote here. So we have d plus root of d. Yeah, so the next part, like we got y prime here, and t plus, alright, multiply by t. What was this here? It was showing that these are functions, yeah. So solutions of t plus y times y prime equals 0. So, right, so that's what we're doing. So t plus, this is where you start showing that this is solutions of that. T plus y times y prime. So y is c squared minus, it is square root of c squared minus t squared. That's multiplied by negative t, which is y prime. Negative t divided by square root of c squared minus 2t squared, So the square roots will cancel out, so you just have, it's all equal to 0 here. Copying out an equation by plugging in. So it's t minus t equals 0, which implies that 0 equals 0. You simplify down. Why? Oh, but that's the positive square root. So if we take the negative square root, the start, it's a little bit simplified work here, but you get y prime equals negative 1/2 times negative 2t divided by square root of c squared minus t squared. Yeah, pretty much instead of a positive 1/2, it's a negative 1/2. That's the only difference here. So you get y prime equals t divided by square root of c squared minus t squared. Yeah, when you yourself take the square root in a problem, generally speaking, you have to consider both the positive and the negative square roots. So this is a good review of all the calc and algebra we've had in the past. And you can show this to be solution So you get the same thing, same process, and y equals plus or minus the square root of c squared minus t squared, therefore is the explicit solution. So we have both the positive and negative square roots. And now in C, we discussed the interval of existence for each of the solutions, part B. So y equals plus or minus square root of c squared minus t squared exists when c squared minus t squared is greater than or equal to 0. That's how a square root works. It has to be positive. It has to be positive number or 0. 0, anything greater than 0, greater than or equal to 0, because it's you can't take the square root of a negative number without getting involved in imaginary numbers, at least. But we're dealing with real numbers, generally speaking, unless otherwise stated. So c squared minus t squared is greater than or equal to 0. We add t squared to both sides. Then we take the square root and we get plus or minus c greater than or equal to plus or minus t, or t less than or equal to z. Or for any given constant c, the interval of existence, one way to look at it is that t is less than or equal to c, based on we have the square root of c squared greater than or equal to the square root of t squared. So it becomes c greater than or equal to plus or minus t. And essentially that means that t is less than or equal to c if you really wanted to go through the algebra of it. But we're not going to worry about that too much. Usually it's a lot more obvious. For any given constant c, the interval of existence is negative c to c in square brackets, meaning that includes negative c and c and everything in between. As we basically consider plus or minus c greater than or equal to plus or minus t, because of how that works. Nothing to say. Basically, I think one way to think of it is like you divide by negative both sides. You have to reverse it so it's c less than or equal to t, or something like that. But it gets complicated because of that. But t is basically confined by c is the general idea of looking at it. Basically, t would be greater than or equal to, t would be less than or equal to positive c, like positive, or t would be, when we have to consider, it'd be greater than or equal to negative c though, and it gets weird, but that's how it works. And then the last part we sketch the solutions for one of these to show about me. For c equals 1, 2, 3, 4, different values of the constant c. And you can square this to basically get y squared equals c squared minus t squared. Basically, so we have y squared plus t squared equals c squared, which was part of the original thing. And that's the circle, that's the equation of a circle of radius c. So it's just circles of different radiuses equal to c. Here's one that's more interesting, another one similar. Show that y at t equals 3 divided by 6t minus 11 is a solution of y prime equals negative 2y squared, with y at 2 equaling 3, and sketch the solution and discuss its interval of existence. This is similar to, we have a specific point y2 equals 3. Later on you'll get these initial value problems, so this is a little bit more of a different type. This is like a prequel to the initial value problem type, having you think about an interval of existence and stuff. But an interval of existence is basically where the solutions will lie that actually exist and matter, and therefore matter for any discussion. So we have y prime equals negative 2 times y squared is our differential equation here. So we start with y at t equals 3 times 6t minus 11 raised to the negative 1 power, because you can bring that up. To take the derivative, it's easier to do it that way. Otherwise, you have to do like the quotient rule. And it's easier just to do stuff like product rules and other types of simpler calculations. But this time it's just 3 is a constant, so it's the derivative of 6t minus 11. So 3 times negative 1, we bring out the negative 1, multiply by 6t minus 11 to the negative second power, and we multiply by derivative of 6t minus 11, which is a 6. So we get y prime equal to negative 18 divided by 6t minus 11 squared. When it's all simplified down. And we plug into into the equation y prime equals negative 2y squared. So we have the y prime here, and then we have y at t, which is 3 divided by 6t minus 11, and that's squared, negative 2 times it basically. So and then we simplify down to show we get negative 18 divided by 6t minus 11 squared equals negative 18 divided by 6t minus 11 squared, and so it's a solution therefore. We also have to show y at 2 equals, if we plug in 2 for a value of t, we get 3. So y at 2 is equal to 3 divided by 6 times 2 minus 11. Because this has to, so y at 2 is 3 divided by 12 minus 11, so that's 3 divided by 1, which is equal to 3. Yeah, initial condition of y at 2 equals 3 is satisfied. And I don't think we sketched the solution, nope. So we're just going to talk about into it. I think we can ignore that. You generally don't have to do that on a test or anything with paper and pen and all. Many professors don't like to do that, make you have to sketch by hand nowadays. So it's not a big concern. So y at t equals 3 divided by 6t minus 11 has, from this we can gather that 6t minus 11 does not equal 0. So that means 6t cannot equal 11 because you add 11 you get. And so t cannot equals, and we divide by 6. T cannot equal 11 divided by 6. So we know the point t equals 2 and y equals 3 exists. And 2, we also know that t cannot be 11 over 6, 11 divided by 6. We need 2 to exist. So 2 is greater than 11 sixths. This is like the only restraint we have is that it cannot be 11 over 6, and we have to have this initial value of t equals 2 included. So 2 is greater than 11 over 6. So it implies that the interval of existence is I with a dot above it for interval of existence where I'll use. So it's equal to, we have the lowest point being 11.6, and it can go on to infinity. So any value that's greater than 11.6 this means. So that's why it's parentheses. Parentheses for infinity and parentheses for 11.6. It can't equal 11.6 but anything greater than it. We have to choose which cutoff point, and 11.6 is that. And finally, for these last two examples, we use the general solution and initial condition to find a solution of differential equation. And we discussed interval of existence briefly. Look at what it should be. So this is initial value problems basically, and you'll see these quite often. It's like the number one thing you can get out of this is how to do an initial value problem. So we have y prime plus 4y equals cosine t, and y at t equals 4 divided by 17 cosine t plus 117 sine t plus 3 times c times e to the negative 4t, and y is 0 is equal to negative 1. So we plug in y of 0 for y at t, so it's y of 0 equals 4/17 cosine 0 plus 1/17 sine 0 plus c times e to the negative 4 times 0 power. E to the 0 power is just 1, so basically this becomes plus c, as we'll see. Whenever you have that, it's a common saying in differential equations to take t equals 0 because of that, because it cancels out the exponentials and makes a cleaner solution in examples. And then, so y of 0 is equal to negative 1, though we know that as well. So negative 1 is given for y of 0. It's equal to 4/17 we basically get, plus 1/17 times 0, so that's 0. 4/17 times 1 is 4/17. So basically we get negative 1 equals 4/17 plus c. And so c is equal to negative 1 minus 4/17. And we simplify down to math and algebra to get c equals negative 21 divided by 17. Negative 21/17. So the solution is just found from that because it gave us everything we just had to plug in to figure out what c is. We generally, when you solve this part of the problem, when when you have your solution to the differential equation, the general solution in terms of like was a constant in it, and you have your initial value and all that, and you have your original differential equation, you can use, by that point, you can just find C using the initial value. You'll usually have to solve the differential equation first, but this time they give you the solution, so you can find the exact one. So we just plug in this for C, negative 21/17 to this ln y at t expression. And y at t exists for all values of t, so interval of existence is negative infinity to infinity. Make sure you use parentheses and not brackets. And here's another one. We have ty prime plus t plus 1 times y. So this expression in parentheses y is equal to 2t times e to negative t. And y at t is equal to e to the negative t times t plus c over t. C divided by t right there. And y of 1 equals 1 divided by e. So t so y of 1 is equal to e to the negative 1 essentially, because t is equal to 1 in this case, times 1 plus c over 1. So basically 1 over e we plug into it is equal to 1 plus c divided by e, and we can just cross multiply to solve for c. We get e equals e, because it's e times 1 is e, equals e plus e times c. I'll put that in. E times 1 plus c is just e plus ec. Then we subtract e on both sides to get ec equal to 0, divided by e there, both sides, and we get c equals 0. So y at t is equal to e to the negative t times t plus 0 over t, so it's just y at t equals t plus 0 times e to negative t, so just t times e to negative t. So we can put that in the bottom denominator, so it's t over e to the e to the t power. Or you can also write it as y at t equals t times e to the negative t power. Generally speaking, they're both acceptable forms. The negative exponents aren't always liked, but a lot of times we deal with them as part of it, and it can be left alone often enough. So yeah, so y at t equals t times e to negative t is also an acceptable answer. An interval of existence is negative infinity to infinity here, because there's no real restrictions on the solution. And it's only because the actual thing is t times e to negative t. Like, as we know, the exponential function never is 0. Like, it can get close, but it never will be 0. So, like, e to the infinite power is infinity, but e to the negative infinity is 0 when you take the limit. But you'll never reach that. So it's always going to be a positive number. The exponential of e to the negative, regardless. E to the any power, negative or positive, it'll always be greater than 0. And then even applies, that's why t divided by t is at. But, alright, that's it for this section.